Hello, good morning.
Hi,
How are
how are
you?
you?
Doing good. So while I'm getting some stuff set up for calculus, what you got going on the rest of the day? Anything cool, or is it just all calculus?
Uh, it's gonna be just a calculus day.
Uh, One of those. Yep.
Yeah, I have our homework is always due on Mondays. So this is really how I spend my Sunday, just trying to finish the rest of the homework that I have.
Gotcha. Well, I hope I can help speed up the process and you get at least a little bit of time to relax. But yeah. All right. So what are we working on today?
So we're covering integration
Mm-hmm.
right now. Um, Specifically like indefinite integrals,
Mm-hmm.
antiderivatives, all that stuff.
Yep.
Um, and then the summation stuff in area,
Yeah.
Riemann sums, definite integrals,
Oh, that's
pretty
right.
much.
Riemann sums. Always hated doing those.
Well, I hate doing all of this because it just really doesn't, it does not click with me for some reason.
Okay. Let's take a step back then. Let's talk about integrals. So do you know what an integral tells us?
Off the top of my head, no, but
Okay. So let's say we've got a function. Um
wait, no, I think I know.
okay.
Integrals are like small sections of a function, I think. Actually, I think I might be thinking of something else. Never mind.
Uh so there are small parts of sections with integrals, but there's also small parts of sections with derivatives. It all has to do with kind
Yeah.
of like, you know, the definitions of calculus. Um but the idea with integrals is that let's say we have a function. I'm just gonna do well, not my best drawing, but this is, y equals x. Very, very normal function. If we wanted to, let's say we had this range. So I don't know what this is. I'll call it x equals a and x equals b. And we want to find the area of this area bounded by the function. So we could do this if we know how to calculate the area of a trapezoid, because that's what this shape happens to be. But let's say it was some other function where we don't know what the shape is. We would use calculus to find this area. And so one way we can think about this is so what Isaac Newton thought of way back when is he said, well, if we take a very thin slice. Well, actually, so it's like, all right, what if we do a Riemann sum, or like a left sum, right sum, mid sum, whatever, and we do this sum, we'll get about the area. It's gonna be not exactly the area, right? Because there's a little bit of overhang and underhang, but we'll get about there. But what would happen instead if we made these rectangles infinitely small? We took a bunch of infinitely small widthed rectangles and then smushed them all together. Um, what Isaac Newton says is that if we do this, take a bunch of these really small rectangles together, compress them together, um, and we would say that we write that as the integral of from a to b of the function. So I'm going to say the integral as the function is f of x, where d of x is the width of the small rectangles. This produces the area underneath the curve. So that's what's really happening with these integrals, and that's why we use them. because we can find the area of whatever shape we want as long as we have it bound by a function or a couple of functions. In addition with these kinds of functions, so if we have it as just f of x, it'll go all the way down to the x-axis, and that's what the area will calculate. If we have multiple functions, like let's say we kind of have like an x squared graph that intersects, well, I didn't draw it very well, but imagine that it intersects at A and it intersects here at B. If we wanted to calculate, I'm going to put it in blue. If we wanted to calculate this area right there. So right now, our only tools available to us is just kind of like the standard integral. So right now, if we want to calculate this area, we don't know yet exactly how. So this is like the area between curves. Have you talked about this yet?
I don't think we've talked about between curves
Okay,
yet.
okay. Um, might be getting a little bit ahead of myself. So I'm guessing then you've been doing Riemann sums, maybe different kinds of sums like left, right, middle, maybe trapezoid sums. And I think there's like a Stevens or a Steffens or something like that sum, where it's like the numbers are kind of weird. I forget what that one is called. Um, and then you've just gotten introduced to integrals.
Like we've been doing Riemann sums and definite integrals.
So I guess I'll ask you this then. So what about integration is giving you a problem? Is it like the calculating? Is it just like you don't understand what it is?
It's like literally not knowing how to approach it, or I don't know. I feel like the way my professor has been explaining it, like, and the work that he shows to provide his explanations, I don't know. It's just not
Okay,
clicking for some reason.
sure. And so it's mostly just, if you're given like a definite integral, you're not sure how to, compute it.
Yeah.
Okay. Yeah, we can do that. Are you pulling up a problem? Because I could also pull up a couple of problems. I just don't want to overlap.
I can pull up some problems.
Okay. If you have problems in mind that were giving you trouble, those would be good to go over. I also have some other stuff as well.
So something like this.
Okay. All right. So we got the Oh, so these are indefinite integrals. Okay.
Yeah, we've learned indefinite, definite. Indefinite was the first thing that we learned.
Yeah. Okay.
Like, I feel like I would do better if I like knew the exact steps to take
Mm-hmm.
when solving any of these problems because I feel like I'm not really given any steps. I feel like we're just given like the definitions and then he shows us an example, but
Yeah.
I'm just like, oh, I can't keep, I can't follow.
Sure. So go ahead and stop sharing your screen. I've got the problem. So do you know what I believe it's called the power rule is for calculus?
Yeah, it's like the exponent times what's in the function times the derivative. Or am I thinking of something else?
Uh, I think I think maybe what you're thinking of is the chain rule. Um,
Okay, yeah, I'm thinking of the chain rule.
yeah. So the power rule when we're taking a derivative. So if I take a derivative of x to the n, the power rule says that this derivative is equal to n times x times n minus or x to the n minus one. Is this familiar?
Oh, yeah.
Yeah. So,
Yeah.
so like if we have x squared,
Okay, yeah,
the
that's
derivative is 2x.
yeah.
Yeah. Um, Likewise, if we take the integral of x to the n, so this is the power rule for derivatives. This is the power rule for integration. The power rule for integration tells us that x to the n is x to the n plus 1 over n plus 1.
And that gives the antiderivative.
Yep. So this is just the answer. If you have any polynomial function, you can just do it like this, and then you'll get the answer spat out. So if you have the integral of x cubed, what will you get as your output?
So x to the fourth over 4.
Yep, just that easy. And another thing that'll be very helpful for you to know is that the derivative operator and the integral operator. Oh, actually, this should have a dx here. There we go. Now it's written out properly. But back to what I was saying. The derivative operator and the integral operator are what they're called linear operators, and all that fancy math language is just to say that if we have the integral of x squared plus x plus 1, a quadratic dx, we can split this integral into three integrals: the integral of x squared plus the integral of x plus the integral of 1 dx. And you see that we can apply the power rule to each of these individual integrals.
Mm-hmm.
I believe you're familiar with doing that for derivatives, where if we have like the derivative of x squared plus x plus 1, you can take the derivative of each individual term with the power rule. These are the kind of two basic ideas you'll need for this problem. First one is the power rule of integration. The second one is you can apply the integral linearly. I'll kind of walk you through this one. So for this problem, let's apply linearity. So we're going to have the integral of square root of x dx plus the integral of 1 over 2 square root of x dx. Then I'm going to, well, actually, are you familiar with the fact that we can pull out constants in integration? So like I can take the 1/2 inside here and
Okay.
then bring it to the outside.
Yeah, he was doing the same thing.
Yep. Yep. It's just a property of derivatives and integration. We can pull them apart like that. So let's look at this one, the integral of square root of x dx. How can we apply the power rule to that integral?
So that is just x to the 1/2 power.
Very good. Yep.
So it would just be, let me not do mental math because I know I can't do mental math like that. Well, 1.5. Well, no. Yeah, I knew. So it'd be x square root of x over 1.5, right? 1/2, right? Or one and a half.
Yeah, 1.5. Um,
Mm-hmm.
so it's going to be, I'll write it like kind of how you said it. So it'll be x to the 1 plus 1/2 all over 1 plus 1/2. But I'm going to write this as x to the 3/2. Then if we have 3/2 in the denominator, we can flip that up to be 2/3, because 3/2 is in the denominator. All good here?
I think so. Yeah.
Okay. And then let's look at this one now. So we have that 1/2. And what is our exponent for this problem?
It's 1/2 again, right?
Yep, but not just 1/2, because if these were both 1/2, they would be the same, but they're a little bit different. What's the difference?
Why are you asking what's the exponent? Wait,
Oh, yeah, of this whole thing.
of the whole thing? Okay. Um, with the power rule?
hmm Yeah, because we need to know what the exponent is in order to do the power rule.
It's, I don't know.
That's okay. So 1 over square root of x Um, so you kind of had it right. It's going to be x to the 1/2. That's all true. But one of our rules of exponents is that if we have a term with an exponent in the denominator, we can write it as -1/2, and then it's in the numerator. So another way you can think of that about this is that 10 to the -1 is equal to 1 over 10.
Okay.
This here is going to be the exponent from which we're going to use our power rule. So we're going to have x to the -1/2 plus 1, which is just 1/2, and then divided by n plus 1, which is also 1/2, but I'm going to flip it up so it's out of the denominator. So these twos are actually going to cancel here, and we're left with x to the 1/2. And we're doing indefinite integration, so we have to add a constant.
Plus C.
Mm-hmm. And this should be our answer. We might be able to do a little bit of factoring, but it's not going to change the answer significantly.
And you got 1/2 times 2/1.
Mm-hmm.
How did you? I think I'm missing that. Where did the 2/1 come from?
Excuse me. I'm also having some oats in the mid morning.
Oh no,
Um,
you're fine.
so we had x to the 1/2. This is after we've done our integration. So we had x to the 1/2 over 1/2. One of the, I guess, properties of division is that, and of multiplication really, is we can convert between division and multiplication if we change our operation by the reciprocal. So what I mean by that is we can go from dividing by 1/2 to multiplying by 2.
Okay.
Yeah,
Okay.
and if you think about it, if you divide a number by like a decimal, like 0.25 or zero point 0.5 in this case, the number gets bigger, right? Just because that's what we're doing. So really, the 1/2 turns into 2 times x to the 1/2, and then I write the 1 just to show that operation. Does that make
Okay.
sense, or is that still not working for you?
No, I think it makes sense.
Okay.
I think that was. I understand the steps. So like a good step would be to like separate the integrals
Mm.
and then like yeah, separate the integrals and then find their antiderivatives
Mm-hmm.
and then that's it.
Yeah.
And combine. Okay. Okay.
Yep. You gotta add your plus c,
Yeah.
and if you're doing an indefinite integral, you can stop here. But if you're doing a definite integral, then you would have to um, apply the bounds, and then you'll get a number.
Yeah.
But yeah. Yep. So that's it. Let's see. Is there anything else? So I will kind of talk briefly about kind of the difference between derivatives and integrals. So like with derivatives, we had a whole bunch of techniques. We have, we can apply it linearly. We can, we have the power rule here. We have the product rule, the quotient rule, the chain rule. We got a bunch of techniques in order to solve a derivative. So most derivatives, we can actually do right from calculus 1. There aren't any more derivative techniques that we learn that aren't like for much much higher maths. Like I'm thinking on the span of like calc 1, calc 2, 3, 4, so on. Um but well actually, do you know if you're going to be taking calc 2? Okay. Then
I'm
I'll
not.
be more brief. But calc 2 is the class is all about different techniques for integrating functions. So if you remember, you maybe had like a couple of units or whatever dedicated to how to take a derivative and all of its properties. You need a whole class for integration.
Yeah.
So for whatever reason, the math gods said it this way. Integration as a concept is just so much harder than derivatives. So it's not like it's something you can math out. It's you need to have either the integral already solved for you, or you need to have a very specific integral that's already been mapped out for you. So if it's not a polynomial, and if it's not an integral that you know right off the bat. So, for example, I'm not sure if you've been taught this yet, but the integral of 1 over x is the natural log of the
Yeah.
absolute value of x. So like if it's not something you can look at and go, "Ah, I know what this integral is." At this stage you probably can't integrate it. So, what that means is you need to turn it into something you know how to integrate. And oftentimes that's going to be turning it into a polynomial. But sometimes it's, maybe you can turn it into a natural log of x. Um, if you've done any trig stuff, you might be able to get away with like using a trig property to reduce it down a bit. Um, I don't know if you'll be talking about use substitution, but that's like there's maybe like three techniques. There's like, can I like one? Do I know how to solve this? If I do, great. The other is, can I reduce it into something that I know how to integrate? If so, great. I'll do that. And the last technique is like use substitution. Have you learned that yet?
Use substitution. No.
Okay, then I won't talk about that anymore. Okay, so let's just keep practicing with taking derivatives then. Not derivatives, integrals. So you said you've done a lot of practice with definite integrals, or would you like some more practice with those as well?
I'd like practice with definite, indefinite,
Just
all
integrals.
of it. Yeah.
So before we even start trying to solve this, how are we going to write out the integral?
Um, each term, so the integral of 6x cubed dx
Sure.
minus the integral.
Yeah, I was just saying we would write integral from 1 to 3
Oh,
is, yeah.
yes.
Yeah,
Okay,
I'm
yeah.
talking about like very, very beginning. But you're right. That is the process we're going to do. And then we can do. So when I'm doing definite integrals where there's a lot of pieces like this, I'll just write the integral of 6x cubed, and I'll pull out the 6 out front. And I'll leave the bounds off until the end, because we're evaluating all of these from 1 to 3. Well, you might be learning substitution pretty soon, because at least in my textbook, it's the next thing after integration formulas.
The last thing that we've learned is the fundamental theorem of calculus.
Okay, so maybe you got a couple of topics before then. Good old fundamental theorem of calculus. Yeah, let me know once you got integrals for these things.
I have 6 uh, integral or squiggly uh, x to the fourth over 4
Mm-hmm.
dx
Nope.
minus,
So no dx. So once you integrate, the integral on the dx will go away.
okay, no dx. And then minus 4 x cubed over 3 plus 2 x squared over 2
Mm-hmm.
minus, is it just going to be minus 3?
So this one's kind of interesting. So because there's no x, um, well there is an x, but it's kind of invisible. Our x here is x to the 0.
Okay. So it'd just be X over 1.
Yep. So minus 3x. I'm not gonna write the over 1 part. Okay. And then we're doing a definite integral, so these are gonna be evaluated from 1 to 3.
Is this like the f of b minus f of a?
Yes.
Like capital F?
Yeah. Capital
Okay.
F for it stands for the integration of the lowercase. Yep.
And then literally just solve.
Yep. Literally just solve.
I got 262 over 3, or 87.3.
Mm-hmm. That's right.
Okay. And this doesn't involve plus c.
Correct. No
Okay.
plus C for this one.
And that was it? So for this, is it literally just like the same steps with the indefinite, just but you're just plugging in the interval
Mm-hmm.
when you get to the
Yep.
okay.
Yep. The steps diverge here. We're with for definite, as you said. We'll apply the bounds. Then if it's indefinite, we add the plus C. So I'm just kind of curious. Do you know where the plus C comes from?
Mm, I don't know where it comes from. I just know what it is. I just know it's the constant.
Yeah. Uh, I'm gonna show you briefly. So I like x squared as my function of demonstration. So we got x squared. Its derivative is 2x, right?
Yeah.
So let's say we have x squared plus 1. What is the derivative of x squared plus 1?
Just 2x.
Yeah. So you see, if whatever number here we add, the derivative is always going to be the same. I could do a billion, it'll still be 2x. But the problem is, if we're integrating, we're going from 2x to x squared, we don't know what this value is supposed to be. So we say plus c and just kind of, we know it's a number, we just don't know which number.
Mm-hmm.
So that's where it comes from. Does that make sense?
Yeah.
Yeah. So have you learned any special integrals so far?
Um,
So we have like the power rule, which tells us how to find polynomials. X to the n plus 1 over n plus 1. Um, there's the 1 over x, natural log of x. Are there any other integrals that you've learned so far? So maybe like trig functions or anything else?
we haven't learned any special ones.
Okay.
Or let me or hold on. We've learned like different properties.
Okay. What kinds of properties?
Like if f is defined or no. Well yeah, if f is defined at x equals a, then the integral from a to a, f of x dx equals 0.
Oh, yeah.
But like,
Okay. So like if I gave you the integral of sine of x, do you know what this would be or no?
is it negative
Yeah.
cosine?
Okay, so you have done trig.
Yeah.
Okay. Yep. Yeah, we got our polynomials, our logs, our trig, and then there's also kind of one other. It's if we have the integral of e to the x. Do you know what
Oh,
this integral is?
it's just
Yeah.
e to the x again. Yeah.
Yep. Very good. Okay, so that's all good. Have you talked about integrating even and odd functions?
I do not see that in my notes.
Okay, that
So
that
no.
might be right after where you guys are at.
Yeah, the last thing we took note of was just the fundamental theorem
Hmm.
with the capital F of B minus capital F of A.
Hmm. Yeah, have you talked about the mean value theorem?
Yeah,
Okay.
but you could explain that again because I still am wonky with that one.
Yeah, sure. So the mean value theorem is very similar to what we've been doing so far. So, if we have a function a to, and yeah, if we have a function on the interval a to b, then the integral of this function is a to b of f of x dx. Good so far?
Uh-huh.
The mean value theorem says if we also tack on a 1 over b minus a term, uh, this actually produces the average value of the interval. If we have, for example, yeah, why not? Let's do sine. That'll be easy to show. So if our interval is from 0 to 2 pi, it's it's kind of clear to see that the average value is going to be 0 because these 2 points are going to oppose each other and so forth and down the line. If we had a function where that's not so clear, like I don't know what this function is, but it's something like this, or maybe we're trying to find over this interval period what is the average value. We could use this and it'll say, I don't know, maybe it looks like it's about this. Maybe that's the average. I don't know. If we had this function, we could find out exactly. So that's what it does. In terms of math, it's basically the same. We're going to calculate our integral because it's a definite integral. We're gonna, apply the bounds, and then we have a 1 over b minus a term that we're just gonna multiply to everything at the very end. So does that make sense?
I think it does make sense.
Okay.
One.
So let's do real quick. So let's say we've got 8 minus 2x over the interval 0 to 4. What's going to be our average value?
Would it be 1/4? Like, am I just plugging that in to that?
Yeah. So you have, or so we have, so the integral is 0 to 4 of the
Yeah.
function 8 minus 2x dx. We have that term, the 1 over 4 minus 0. The average value is going to be all of this. So you'll have to calculate the integral.
Okay. So it would just. So would that be 1/4 um the interval AX?
Mm-hmm.
Oh, yeah. So was I not supposed to, like, I did 1/4 integral 8 minus 1/4 times 2 integral x because of the 8 minus 2x.
Um, so you can take the 1/4 and put it in, but there's no reason to. Um, because it'll well, I don't know. Yeah, you can do it either way. I guess it doesn't really matter. So you can either put the 1/4 in, and then it'll be, um, 8 over 4 minus 2x over 4, and then do the integral that way. Or you can leave the 1/4 on the outside. It'll be the same thing. I usually like to leave my constants on the outside if I can. Then we got to apply our bounds. Yep. So Not much different process-wise.
That made sense.
We got time for one more. This will be an interesting integral. You see that all right?
Yeah.
Okay.
It's the same steps.
Yeah, basically. So what's
Like
the
I can separate this.
well, not right now. So what's
Yeah.
the problem with this integral right now?
You said what's the problem with it?
Yeah,
Um, it's a quotient
yeah,
and not like easily. I don't
yeah,
know how to put
yeah.
it.
It's we. So the most basic problem is we don't know what this like. We don't have an integral that looks like this as a part of our repertoire. We need something like this. So we got to do algebra in order to make it look like this kind of. So what we can do is one of our properties of fractions is we can say that x minus 1 over square root of x is equal to x over the square root of x minus 1 over the square root of x. So this is like going back to fractions in like middle school or whatever. We can use the same concepts. And then
Okay.
we can reduce these. So we're going to have square root of x minus 1 over square root of x. Hey, actually, we did this integral earlier today, didn't we?
Did we?
Yeah, we did
Oh
a
yeah,
square root of
we
x
did.
and
We
yeah,
did.
yeah. So we don't have to do this one. We're almost out of time anyways. But so this is the idea is if we see an integral and and if it's a polynomial, we're great. We can do it instantly. Or if it's a special integral, like if it's sine of x or 1 over x, we know what those are. We can do those as well. But if we look at it and we can't, then we need to do some sort of algebra to make it look like what we need. Um, at this stage, you probably won't be given any integrals that you can't do.
I hope not.
Once we get to u substitution, then things will get a little bit more tricky because we can do problems that we can't normally do, because the technique is a little bit more, uh, special. But yeah, any other questions before we end off for today, or are we good?
That was good.
Awesome,
That was good. I feel like I'll be able to do my homework now.
cool. All right, sounds good. Then I'll see you next time. Kari, is that how I say your name?
Yes.
Cool. It's
Yeah.
actually pretty close. It's mine, Carl, Karl. I remember like sometimes in the past when I guess my handwriting wasn't the best because like sometimes people would say my name is Kari, so I think the L is an I.
Well, nobody ever knows how to say my name, right?
Yeah,
They always want to enunciate the H. Kahar.
Kahari.
Yeah. Like that doesn't even sound good, and you guys know.
All right.
But thank you, Carl. It was nice meeting you.
Yeah, it was nice meeting you too. I'll see you next time.
Okay. Have a good one.
You too.